In this video, we're going to discuss energy. Just to start off, what is energy? Energy is basically the ability to do things. You have to have energy to make changes. Without energy, something will just stay as it is. Let's think about types of energy that we kind of see and are used to. There are different types of energy. A common one is kinetic. This is the energy of motion, being that we are moving creatures that walk and talk and throw and tumble and fall and climb. We are generally pretty okay with the idea of kinetic energy. A lightweight object that's thrown and hit you hurts a little. A heavy object that's thrown and hit you hurts a lot. We're used to the idea that, a heavier thing moving at the same speed hits harder, has more energy. Similarly, a car at slow speed can still hurt because a big mass, even moving slow, has a lot of power behind it. And a car moving fast is extremely dangerous. We just kind of have these general ideas of kinetic. We are comfortable in passing with the idea of how mass and speed play together with how much energy something has. Well, beyond kinetic, we tend to be fairly good with the idea of thermal. How hot is it? How cold is it? Can you make something hot? Burn some methane and the water starts to boil in your pot. Throw another log on the campfire, it gives off some heat. Generally, the idea of thermal energy is something that we're reasonably okay with. Additionally, put your hands together and start rubbing them. They'll start to warm up. Rubbing your hands together can make them warmer. Put your hands near each other but not touching, and do the same back and forth motion. You'll notice they're not getting hotter. If they're not in contact, you don't get the thermal change. You're still moving them, you're moving and releasing kinetic energy, but it's not turning into heat. It's not turning into thermal energy. And that's the key. We can turn one type of energy into another. Kinetic can become thermal if you have the friction of your hands together. If your hands are only near each other, moving back and forth, they're not in contact. There's no change. Energy often is about conversion. There are different means of converting types of energy between each other, and those are kind of all of the devices that we build. We'll talk a lot about them, but the types of energy, but there are more types of energy that you can convert between. And the one that's most important for chemistry is potential. We often think of potential more like a rock on a cliff. There's some rock up here, and it sits there for a long time. But sunlight, rain, wind, eventually, the wind might come in and blow it and push it away, and that rock will tumble and roll down the hill. Once it's done that, it stays down there. How often have you ever seen a rock roll up a hill? It doesn't. Why does it go down but not go up? Well, to move down the hill, it had to have kinetic energy. When it first starts at the top, it isn't moving at all. You could touch that rock and it wouldn't hurt you. But if you were hanging out down on the bottom and that rock starts rolling down Indiana Jones style, you're going to get out of the way because it has a lot of kinetic energy as it comes down that hill. So it gained kinetic energy. It did it by going down in altitude, down in height. Because gravity is always pulling down. The only reason the rock hadn't gone down further to start with is it got stuck on top of the hill. In fact, even sitting here, that rock is being pulled down. There's just stuff in its way, and so it can't fall any farther. If you were to have this be on top of a mine shaft with a small little wood panel top, that rock might be heavy enough to break the wood panel, and then the rock would just fall down further. As soon as it's possible to fall down, it will, because it is always being pulled by gravity. Well, it's being pulled in one direction. To go the other direction, it has to work against gravity. Gravity is trying to prevent it from going up by always pulling it down. So why did that rock roll? Why did it move at all? Because it had the ability to be pulled down by gravity, but it doesn't have the ability to be pulled up by gravity. And so it had the potential to go farther down. It had the potential energy stored waiting at the top of the hill to change its elevation and have gravity pull it so much further down. As soon as it got over the edge where it could start to move, that potential turned into kinetic. It rolled until friction brought it to a standstill at the end. As a rock rolls down the hill, it bumps into things, it pushes off of them, it pushes a few out of the way. Some of the kinetic of the boulder gets lost by pushing other things, but it also just heats it up. So some of that kinetic that was created when it started to roll is lost as thermal and kinetic to other objects until it finally comes to a stop. Why is potential so important? Well, potential is what is stored in chemical bonds. If we think about chemical bonds, what makes a bond? The simplest view is I have a proton, and around that proton are electrons. Well, originally your atoms are separate. So say this is a hydrogen and a hydrogen. But if we bring them together, we can make dihydrogen. They can bond to each other. The reason this works is if you overlap the orbiting electrons, you end up with some attraction of that electron, not just to its own nucleus, but to the neighboring nucleus. You have opposite charges, and they are attracted to each other. When that electron starts moving towards the other nucleus, it drags its own one along with it. The net result is those nuclei get closer. Now there's an ideal distance. If they get too close to each other, then what happens is the protons get too near and you start repelling. If your positives get really close, they'll shove away. But there is some ideal distance where they are reasonably stuck together. If the nuclei try to move apart, the electrons will draw them back towards each other. Well, if you ever held two magnets a little distance from each other, there's a slight pull from each other. But if you got them a little bit closer, there was a big pull from each other. The closer you can get opposite charges, the more attracted they are, and it's an exponential. It is not a linear change. Half the distance is not twice the attraction, it's many times more. So slight changes in the distance between nuclei and electrons can have a massive change in how attracted they are. So if you ever held two magnets near each other, and you just let go, assuming they were close enough, they will stick to each other. The magnet wasn't pushed by you, it just pulled the other magnet. They somehow create kinetic energy. And you can't create energy. It really had to be converted from something. So where on earth do those magnets get the kinetic energy to move towards each other? Potential. Because there's a plus and a minus side of each magnet, and opposite sides are attracted, they will pull towards each other. Well, the closer they get, the stronger that pull, which means it's that much harder to take them back apart. If it's harder to pull them apart, you've got to put in more work to pull them apart. Well, you can't create or destroy energy. So if you have to put work in to take something apart, they had to give off energy when they came together. How did they give it off? They had potential that turned into kinetic. And so your magnets will come together and contact each other. To break them back apart, you have to put in potential energy to separate them, because they will wait until they're near each other, turn that into kinetic and pull back together. And so charge attractions that haven't been allowed to reach each other have potential. They could get closer together and bind even more strongly. This is what chemical bonds are. Chemical bonds are storage for potential energy. Because you cannot create or destroy energy, all forms of energy that you observe must be converted from some other form. If you can properly track those changes, you can know how much energy was expended by a reaction. If you do something like CH4 plus 2O2 into CO2 and 2 water, well, it gives off energy. It gives off heat. That's why we burn methane. We want to release heat up some water, or whatever else we're trying to do with it. If you know the amount of energy given away as heat, well, it had to come from somewhere, and it came from the chemical bonds reorganizing. It came from potential. You can actually measure the difference in potential between our molecules, as a carbon and a hydrogen have one length, and an oxygen and an oxygen have one length. As you reorganize and change those balances of distances and attractive forces, you change the potential. Opposite charges have altered how close they are to other opposite charges. It takes differing amount of work to pull them apart. But how would you know the difference between these two? You look to the energy it gave away. This is a fundamental part of being able to track not just chemistry, but all of physics in any way. The whole universe has a consistent energy. And so within any specific reaction, if you can track the changes, you can know exactly where the energy must have come from and where it should be going. This tells you how much of something reacted. Because one molecule of methane and 2 molecules of oxygens reorganizing into 1 molecule of CO2 and 2 molecules of water will always give exactly the same amount of energy. It's simply the difference in potential. So by knowing what it's supposed to be, you can predict how much methane you'd need to burn to heat up a pot of water, or to run a reactor at a power plant, or to weld steel. You can actually predict the needed amounts, or if you know the energy released, you can calculate how much must have gone into it. So energy is a useful tool that amounts to accounting. It's just telling us, hey, everything has to transact in a certain amount of energy. Keep track of your energy the way you could keep track of money at a bank. All the ins, all the outs, they need to add up to each other. This is the basic concept of energy. How do we measure it, though? We need some units for it, and the common unit for us is the joule. Written as a big capital J. The joule is a kilogram meter squared per second squared. A mass over a distance at an acceleration. So kilogram times meter per second squared. Combined here into a nice short one. Additionally, sometimes you will see the calorie. 1 calorie is equal to 4.184 joules. Calorie comes up for nutrition more often. Joules comes up for physics and chemistry more often. These are the units that help us measure energy. How much energy is released by something, how much energy goes into it, where they come from. 1 calorie was the energy for 1 gram of water to go up 1 degree Celsius. And so how do you decide what amount of energy to make your standard? Well, it's metric. We use water. And so 1 small metric unit of water, 1 metric unit of temperature change, that gave us our 1 energy unit. Ends up this doesn't follow the standard units very well, and so Joule was created so that everything was based on kilograms, meters, and seconds. But here is where our original energy conversions came from.